Next speaker is Howard Pritchard from Cray. He's a principal engineer in the software architecture group in the high performance computing division, HPCS part of it. And the topic is, let me see if I get this right, I/O characteristics for shared memory applications. Just to relate this back to our bigger picture here, we've been talking about distributed computing. We've heard about the message passing side of it. This is really about the shared memory side of it. So, Howard, drive away.
Basically, what I'm doing is a follow-up to what Jeff Squires had, and which Nathan just summarized. But rather than just for the MPI group, we were collecting feedback from the SHMEM and PGAS, where PGAS stands for Partition Global Address Space program models for this OpenFabrics interface working group. And the first thing I'd like to say, this is a work in progress. I'd say this is a snapshot in time. We're not naive enough to think we can go and talk to a bunch of people who are probably a little don't have necessarily all their thoughts together that day, and expect that to be the final word. So we do view this as an ongoing kind of feedback loop process. Although probably a fair number of the people in the audience know about SHMEM and partition global address space languages, I want to kind of go back and get a second look at them more in the context of the types of hardware features and API features that this group would probably be more familiar with how to do well and how that would couple into these models. Then the core of the talk is this feedback, and I've broken it up into some buckets. Endpoint considerations, where endpoints is kind of an InfiniBand EQ pair or just a generalized concept of that. Some memory registration, a little bit about the different characteristics of remote memory references for the SHMEM and PGAS models compared to MPI. A little bit about collectives, and then active messages. We have the Gasnet LNL contribution there. Ongoing work. So SHMEM has actually been around for a while. It's a library-based for a while, I mean quite a while, since the Cray T3D days. It is a library-based one-sided program model. The only type of program model it supports at this point is single program multiple data. The key concept in SHMEM as far as the programming model is there's what are called basically private sections of your memory, and in these little diagrams up here, these are the processes which in the SHMEM model of a job, some magic has occurred if you're running in Linux with VM randomization on, so it's true magic in that case. Every image has the exact same virtual address space layout as far as the symmetric memory regions go. So up here is the notion of the symmetric heap, these purple blocks. The blue blocks are the data segments of both the executable and in the typical real world nowadays, all the little data segments for the shared libraries that are loaded into the image. And the main concept is a symmetric memory region. So if, for instance, in your application, you have a data buffer in your private heap in rank 2, and you want to put it into a data buffer in PE0 in the symmetric region, this rank already has all the information it needs to know based on its address for that same object in its BSS, how to initiate an RDMA transfer from a buffer up in this region down to an array in the BSS of rank 0. And likewise for the symmetric heap. There have been a bunch of vendor-specific extensions to this because it's been a rather unorganized cacophony until recently as far as this programming model goes. Quadrix, for instance, added a bunch of stuff to SHMEM. But there has been an effort recently initiated by various organizations, one of them being Oak Ridge, to try and standardize and kind of herd in all the cats that have been going on with this model. And I think part of the motivation for that is kind of going back to Dr. Sterling's talk yesterday. This is being considered as a potential MPI plus something else for exascale for those who want to kind of just keep on doing what they were doing with something else. UPC, this is another variant, and I'm not planning to do a comprehensive survey. These are just the ones we first wanted to focus on. UP stands for Unified Parallel C. It has a similar notion to SHMEM, but it's compiler-based, and it's not something like OpenMP where you just do your C code and look for parallel loops and add pragmas. You have to do more than that. Did you get the? I guess we didn't get to work. Okay, so I'm stuck up here. It has a notion kind of like the old high-performance Fortran, where you can distribute these. Can everyone still hear me? In the room? No? Okay, then I'll move back up here. Sorry. Yeah. It has this notion of you can specify arrays that go into the shared address space as, for instance, cyclic, and this is actually block cyclic. An example, block 3 of an integer type X array spread across the shared address space. Yeah, it's actually, okay. And then there's a separation in this model, a strict separation between private and shared address spaces. Great. Okay. Did you get it to work? Okay, too bad. Can everyone hear me? Can everyone hear me? Okay, great. This is easier. And actually, the reason why I want to point this out is UPC in particular is a way you quickly end up generating, if you have your UPC runtime base sitting right on top of RDMA primitives, you quickly end up generating lots of small remote memory references, particularly for customers who are used to having shared memory machines where they ran their UPC. It has a whole set of collectives, very much like MPI, locks, and that kind of thing. Like MPI, it's evolving over time, but more importantly, it's a tighter community than SHMEM. They have a spec that they will come out with every few years, and the vendors more or less make sure that they're keeping up with the spec. A little side note, but it is a possible complication down the road. In general, nowadays, a thread, they denote their ranks by threads, maps to either MPI or SHMEM PE rank, but that's not always true. Fortran 2008. Fortran 2008 is closer to SHMEM, but it's also a compiler-based programming model. The one complication I want to point out with Fortran 2008, which has been within our company quite a thing to support, is that unlike the other two programming models, Fortran 2008 allows for a blending of the shared and private address spaces. There's nothing illegal about an application having a shared pointer, for instance, pointing to a private address. So there's no reason in Fortran 2008 that an application can't, for instance, transfer directly from any part of its address space into, for instance, the stack of another image if the shared pointer points to a stack address. Okay, now to the community feedback. Okay, sort of like what Jeff had in his talk, that Nathan's talk, caveats and disclaimers. There is a large degree of overlap between what the MPI community needs and what these folks need. So I'm not going to go into details, but things like the fork, the munmap, and those kind of problems that occur when you have caching of memory registrations in user space. So what I'm going to focus on are more API or requirements that are more specific to SHMEM and PGAS, but there will be some overlap. Another big caveat is there are differences of opinion, just like in the MPI community, although here it tends to be separated between those who want to implement these types of program models over active message approaches, aka Gasnet, versus those who want to sit directly on top of RDMA primitives like the compiler group at Cray. Okay, so some of the usual suspects. Actually, in the original talk in the working group, I annotate a lot of this with what I was thinking mapped fairly closely to what libfabrics does, but I decided it might be better to leave that out for purposes of simplification here. But nevertheless, the version of this you see up on the download site right now has lots of references to things that are already in libfabric that Sean talked about earlier, where I think the libfabric kind of matches here. First of all, endpoint memory usage needs to be scalable. So, for instance, what Rich was just talking about with dynamic connections sounds very useful for these program models. If possible, a low overhead mechanism for enumeration of endpoints. And what I mean by that is being able to, rather than having to address by looking up some lid number for every rank you want to talk to in a big table, just be able to generate on the fly the address that you need to do an RDMA put to, for example. re-emphasizing great to be connectionless, yet reliable style endpoints. If connected style endpoints are the only choice, especially for UPC, it would be very good to have an efficient way to do a full wire up at the beginning of the job. This last bullet is actually quite important, and I do hope this is a case where we might miss the boat if we aren't careful. The OpenSHMEM group just earlier this month was meeting in Maryland, and there were actually several talks about this. As we go forward with these nodes which have more and more cores, there's no way that we're going to be running a SHMEM PE or an MPI rank on every single core. So we're looking at highly multi-threaded processes on each node, wanting to use some communication conduit between the nodes. And if you had to do something even like what we have to do today on MPI with thread safety initialized, it still basically ends up often being a sequential bottleneck. Now, one advantage these one-sided programming models have is from a theoretical concept, because you don't have these notions of receives that have to be coming in some kind of order. You would think these one-sided models would inherently be superior in that kind of an environment, or much easier to implement. And so what we mean by thread hot here is that we'd want to have some type of object in the API where we knew if we allocated multiple ones of these objects, that the higher level SHMEM implementation, for instance, could treat each one of those as a separate context where you wouldn't have to worry about thread safety, except to control if you had to have multiple threads mapping to that one object. I hope that makes some sense, because this is actually an important point. This is I don't want to miss the boat point. Memory registration, not too much new here. I think most of the people who were involved, and I do have a list at the end, I moved that to the end to save us time, of the people who participated in our last telecon. They recognize that in a lot of our hardware for today, explicit memory registration is probably the right thing if that's the way to get good performance. However, one of the things they would like to, they emphasize would be really nice, is if the memory registration wouldn't have some kind of unscalable component to it, where, for instance, getting back to that SHMEM picture, you had every rank's BSS was accessible in a one-sided fashion by every other rank. Well, it'd be awfully nice if the application itself could assign a key value to, for instance, each of the BSS sections on each local rank within the larger job on a node. So, for instance, if you wanted to send a message to node 5 and there were 5 PEs on that node, then BSS base, which would be the same across the whole job, base plus 4 would get you to the BSS of the 4th local rank on node 5. There is this concept already in libfabrics. Whether a vendor provider could implement it's a different story. Another thing some people asked for was growable registrations, growing both up and down, so you wouldn't have to keep re-registering if, for instance, let's say you S-braked up and you were trying to register not just your BSS, but the base, the heap that grows off the BSS. It'd be nice to be able to grow up without re-registering. We spent some time on the on-demand paging option. There was agreement that this is a good idea and it would be convenient, convenient for some, really good idea for other ones of these models. However, even then, there was a request made that they would still want to be able to do the pinned pages method if that gave better performance. In other words, they wouldn't want to be stuck with this and not be able to do the do-it-myself approach. It was pointed out PGAS compilers may have more control over memory allocation, so maybe it isn't so important for them. Although for this Fortran 2008 feature I just mentioned, and especially for one-sided program models, you could see how they might benefit more from this on-demand paging option. Another thing is the Fortran 2008 in particular, because of that kind of blending of shared versus private address space, what they'd really like is to be able to register large amounts of virtual memory that may only be sparsely populated. So for instance, for our Aries network, we provided this kind of feature for our compiler group because they wanted to be able to sort of pre-prep the IOMU for many, many gigabytes of possible virtual address space registration, but only ended up needing to register small pieces. Okay, small memory reference API requirements. Compared to MPI, particularly if your compiler sits on top of RDMA puts and get primitives. It's really important. They tend to generate lots of small references, many more than an MPI program. So you want, if possible, to have an API which can handle these kind of references very efficiently. Atomic memory ops are important, probably more so in some cases than it was for MPI, excluding the MPI one-sided. I'll talk about puts with various completion notification mechanisms on a later slide. There was a Sandia request for small, partially blocking put requirements, and I think what that really meant is they just wanted to have what we already have, which is this put with inline. I'm not an InfiniBand expert, but I know at least for SINs there's an option for the inline, and I think that's what the request was. There was some work with portals over InfiniBand which generated this request. Oh, here's a fun thing. Now this is for the hardware people to puzzle over and solve for us so we don't have to do it in software. So there's a particular requirement for the PGAS compilers, especially if they're implemented directly on top of RDMA primitives. And it's a question of correctness while also getting performance. So what I'm illustrating here is a potential various read after, well, in this case, it's a read after write and a write after, this is the first operation, this is the second. So this would be a write followed by a read, or a read followed by a write. And here on this side is the initiator, and here's the target. So let's suppose we have to an arbitrary address X, in this top case, the compiler has generated a store, and then it generates, right after that, it generates a load from address Y. And then in the second example, it's a load from address X followed by a store to address Y. So as long as Y and X aren't equal to this given target, the compiler doesn't, and especially in these looser, weaker memory consistency models that UPC supports, it would be great if these two, if one could pass the other. Like if for some reason, let's say by the time you get to the PCI Express, we can't really do, well, yes, you can do this. And let's say by the time the request ends up, assuming you have an HCA that runs over PCI Express, let's say that the upstream posted channel is blocked, but the upstream non-posted isn't. Then it would be great if this could go still in and then come back out, and if the upstream posted is kind of blocked, that's not a bad thing, maybe. But the problem is, what if X equals Y? If X equals Y, then the compiler needs to make sure that these go exactly in order. They can't be bypassing each other. And it really confuses a compiler if it can't assume that. The problem is that most networks actually, if you either get too much order or you don't get enough. And I suspect, so like even in InfiniBand, if you just put fences here, you'd always get the right answer, but you'd get lousy performance, right? So for instance, what the Cray compiler group had to do is they basically have a Bloom filter that goes and checks for any outstanding loads and store operations to given target B. They go through the Bloom filter to see whether there's actually a potential collision between this address and the next one with Y. So if you hardware vendors could figure out a way to do this efficiently in hardware, that would be fantastic, while still giving us performance. And they've also decided they have to keep this because they know that in the future, it's going to be adaptive networks which give the performance, not in-order networks. A little bit about AMOs. Just following up from basically what Nathan said, we need more than fetch and add and compare and swap. There was a request for multiple element AMOs, especially for active messages. Bigger AMOs like 128 bits, so you can have more flexible MCS lock algorithms, for instance. At least two flavors of AMOs. There's the one that we want to be reliable for use with locks and queues, but not necessarily have to do them frequently. And then there's another type for East Coast customers where they want to have at-memory computation, but they only need a good enough answer. They don't need a super accurate answer. So their throughput is much more important than reliability. If a few AMOs fail, that's fine, we keep on going. More granularity in the ops, like 16 or even 8 bits were some requests. There was also a discussion of the AMO cache coherency issues, particularly if you have an HCA that's separated from the host memory by PCI Express bus. It would be nice if there'd be hooks in the API to control the behavior of this cache if it's needed. Oh, there are a few other odds and ends. An important one from the Gasnet folks, they wanted to be able to piggyback message data on top of large RDMA writes, more than 32 bits of intermediate data now. And it would be even great if it was an easy way to, for instance, invoke a remote handler for that message in some low overhead way. They were reaching for the moon, as Jeff says there. Collectives, the main message with the collectives from these folks is they don't like having to keep reinventing the wheel in MPI and SHMEM and UPC over and over again. And they would also like, the general consensus was they wanted something that was flat, so that you didn't have to worry about if the rank that you wanted, some of the ranks in the collective you wanted to use were on node versus off node. And when you listen to these guys and you think about it, I don't think that, I'm kind of in agreement with what Rich was saying. This stuff shouldn't be in this API here. This should be a project sitting on top of something like libfabrics. You could call it libfabc or something, libfabscol, and it would be, sitting on top in a totally different project and not messing up with what's in libfabrics, which, if that's the way we go, that would just provide primitives to efficiently implement this library. Active message support, almost all this is from Paul Harwood, except for the top. There are two types, again, sort of like the AMOs of what you could see for active messages. There might be a lower performance, highly scalable, active message support where you just needed to use active messages for certain kinds of sort of heavyweight operations like UPC Global ALEC. But in things like Charm++, you'd want high performance, and for instance, PGAS over Gasnet, you'd want high performance active messages even for small messages, high throughput. API that would allow, after a queue for sending these messages to be initialized, to be able to send small messages up to about 256 bytes. It would be great if the initiator could get the response back that the message has arrived, and also option to be notified if a callback function that consumed that data had been run. Oh well, this group is excellent at this. Implementation needs to handle transient network errors, messages delivered once and only once to target. And if anyone can do that right, I think you guys can do that right. Right. Some applications may require ordering of messages, but some don't, so it would be nice to have that option. And flow control is important. Okay, so that's the snapshot of where we were. At my employer, we actually are in kind of a good position to help with this effort. We have a contract with the DOE through the Design Forward program, and what we're supposed to be doing is delivering a report within the next few months about a survey of APIs and potential near future APIs and how they would map to DOE application requirements. And so one of the things we're focusing on at the near term is working with DOE Office of Science co-design teams to make sure we aren't missing some, make sure we aren't optimizing some MIM copy in some unused branch of a code. They have this programming model called Legion at one of these co-design centers we want to study closely. They seem to have some particular requirements, they think, for future NICs. And then we'll also be soliciting focused input from the Charm++ and end users of the PAMI API. The PAMI API seems to encapsulate a lot of the requirements for active messages. Here are some references that we included in the old talks. That's it.